In this short video, I would like to present our new paper recently posted on arXiv, where we discover a kind of duality between principal component analysis, which is a popular machine learning method, and quantum mechanics, which is a theory in physics to describe our microscopic world. Let's motivate this work by first looking at some physical fields arising from various physics problems. Here we display the vacuum fluctuation, energy density profiles after having ion collisions, the spin configurations of the Eisen model, and the temperature distribution of the cosmological microwave background. Although they describe a quite diverse spectrum of physics phenomena, they all display local correlation structure. The field configuration in the real space seems kind of hard to study directly. One way to compress the configuration is to decompose it to many basis functions which have good mathematical properties. Normally, the basis functions are chosen orthogonal to each other. For example, the energy density formed after having ion collisions can be decomposed into Fourier basis. And temperature and isotropy in cosmological microwave background can be decomposed into a series of spherical harmonics. Apology for asking a seemingly naive question, but why is that? Why do we use Fourier bases and spherical harmonics in these two problems? More specifically, I ask, in what sense these spaces are optimal? So first, definition of optimal. We have a dataset, that is, we have an ensemble of field configurations. We want an optimal basis to minimize the average reconstruction error for the dataset. Further, if we confine ourselves to orthogonal basis, it suddenly reminds us of principal component analysis, which seeks to explain most variance in data, or equivalently achieves least reconstruction error. Now the goal is clear. We want to prove that the Fourier basis or spherical harmonics can emerge as the principal components of some certain dataset, which contains an ensemble of random fields which have local correlation feature. More specifically, because of the local correlation structure, we use Gaussian process to model the dataset. So Gaussian process is a stochastic process where any collection of random variables phi as a function of x, where x is a point in d-dimensional Euclidean space. The random variables have a multivariate Gaussian distribution. In particular, the two-point correlation function can be defined as Cxy, which has a Gaussian kernel where sigma is positive definite matrix. If we equate x and y, we obtain variance function Ax. The corresponding PCA problem of the Gaussian process dataset can be formulated as equation 2. We first try a non-uniform 2D Gaussian process, where non-uniform means the variance function Ax is not constant. Rather, it's quadratic within a circle, and remains zero outside. We produce sufficient realizations of the Gaussian process, apply PCA to them, finding the eigenmodes, they have some pretty beautiful patterns. On the left, I show 25 different realizations, while on the right, I show the first 25 eigenmodes. The intriguing thing is that if we plot out the eigenvalues, we observe the staircase structure, where the nth staircase have n degree of degeneracy, and the eigenvalue difference between two near staircases is a constant. Such staircase structure actually reminds us of the eigenenergies of the 2D quantum harmonic oscillator. The left plot is the eigenvalues as a function of the index of eigenmodes, while the right plot is the negative eigenenergies as a function of index of eigenmodes. Remember that a one-dimensional harmonic oscillator has a simple spectrum structure, that is, the nth eigenstate has energy proportional to n plus 1/2. And for the two-dimensional case, we view the two dimensions decoupled. So they are just two decoupled harmonic oscillators. Consequently, it's easy to construct the staircase structure. Now, from the example above, there seems a duality between quantum mechanics and PCA. In the following two slides, we aim to give more precise definition of such duality. So equation 1 defines the covariance function. Equation 2 defines the PCA problem. Equation 3 is simply the Schrodinger equation, and equation 4 defines the eigenproblem of the Schrodinger equation. Theorem 1 is the most centric result of the paper, where we state that the PCA problem and the Schrodinger problem, the two problems are the same up to second-order approximation, provided these quantities are equal. Firstly, the PCA eigenmodes correspond to quantum eigenstates. Secondly, the negative variance function is equal to the potential function where the quantum particle lives on. Thirdly, the variance function times the correlation kernel equals to the inverse mass of the quantum particle. The key idea of the proof is to define Rayleigh quotient for the two systems and to see under which conditions these two Rayleigh quotients match with each other. More details of the proof can be found in our paper. Based on this duality, we propose an algorithm called Schrodinger PCA, which aims to convert a PCA problem to a Schrodinger problem. There are three main steps. First, based on the dataset at hand, we calculate some statistics, that is the variance function and the correlation kernel. Secondly, based on the duality, we calculate the potential function and the inverse mass matrix required by the Schrodinger equation. Finally, we solve the Schrodinger equation to obtain the eigenstates and eigenenergies, which correspond to eigenmodes and eigenvalues of the PCA problem. Now it's time we explain how Fourier bases and spherical harmonics emerge from PCA of random field. First, we consider a ring, and both variance function and correlation kernel are constant. Now, the corresponding Schrodinger equation describes a free particle on the ring with eigenstates being the sine or cosine. That's how Fourier bases emerge. In the second example, we consider a sphere, and again the variance function and the correlation kernel are constant on the sphere. This time the Schrodinger equation describes a free particle on the sphere whose eigenstates are just spherical harmonics. That's how spherical harmonics emerge. Let's look at a more non-trivial example. The variance function and correlation kernel depend on theta and phi, and the dependence is parameterized by A. When A is equal to 0, the dependence is lost, and we have an isotropic globe. The eigenstates indeed are spherical harmonics. However, if we choose A equal to 2.9, the eigenmodes on the anisotropic globe are no longer spherical harmonics. The non-zero region in the first few modes imply that the fluctuation magnitude around the pole is larger than that around the equator. The intermediate modes, like the 100th and 200 modes, show there are finer structures around the pole than near the equator. So this means the correlation length is smaller around the pole, which agrees with the ground truth. This example shows the interpretability of the eigenmodes obtained from Schrodinger PCA. Previously, we focused mainly on the interpretability of the Schrodinger PCA, but it also has numerical advantages. Suppose the random field lives in a d-dimensional hypercube. When with size L on each dimension, and the correlation length is sigma, which is often much smaller than L. In PCA, because it requires covariance information among anchor points, two nearest anchor points should be close enough to each other. That is, the distance should be smaller or equal to the magnitude of sigma. Consequently, PCA requires L over sigma to the power of d number of anchor points. By contrast, in Schrodinger PCA, only variance information and correlation kernel is required, so we only need O1 to the power d number of anchor points. So Schrodinger PCA is more sample efficient, and experiments verifying this can be found in our paper. To conclude and discuss, firstly, the dataset does not have to be Gaussian process, it can also be Laplace process. Secondly, we emphasize that although I have argued a lot that we justify the use of Fourier basis and spherical harmonics from the perspective of optimal compression. Thirdly, Schrodinger PCA can be both explainable and effective. Last but not least, it really excites me to think about possible applications of Schrodinger PCA to different physics scenarios. For example, cosmological microwave background, condensed matter physics or fluid mechanics, etc. That's all. I really appreciate your time. If you are interested in knowing more about me, please visit my personal website. Thank you.